All right, let's see if we can make a connection with what I just demoed with the block on the incline with our physics aviary simulation. They've got this force meter, right? They give me a mass, rubber on ice. That's interesting. I could increase my mass, decrease my mass, and you guys notice. So let's just watch it take data. The force is increasing over time. And then it drops down and it gives this nice steady force. Okay, now that's actually pretty challenging to do in real life, but actually not so challenging when we did it with the incline. So what I want to do is put up this graph, and then I believe this should be something familiar from our observations. For those that didn't do, this was basically, this was part 4. A lot of people missed this part. So make sure you go back and resubmit and make your observations about these regions. So a real quick drawing. I have that block, and it's got this force of gravity, right? Now, if I broke it into its components of force, I'd have a force parallel, and I'd have a force of gravity. The greater I increase the slope, the greater this force parallel becomes, okay? So what we observed as we tilted, right, we increased that force parallel, we increased the force, right, and it got to this peak where it still wasn't moving. So region A, if you said the force was increasing, but the object wasn't moving, you were correct, okay? This whole time, right, the block is going to be gripping, right, the surface, whether that's rubber on ice, graphite on graphite. I think I had iron on laminate kind of thing. It's going to be gripping, 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 gripping until there's a point where it can't grip anymore. If you were going to look in microscopically, every surface has bumps. Some have greater bumps and some are smooth. Like ice would be fairly smooth, right? So if this were my iron bar and this were my laminate, right? They have all these ridges, right? Microscopically, and those ridges are holding on, right? Until you exceed this force. Now there's this drop right here, okay? This drop right here. And then all of a sudden this force is nice and steady. When that block started moving, I tried to keep it at the same angle. Did the force of gravity parallel to the slope change? No, but it kept accelerating, so there was a net force down, okay? That means there was a constant force this way, and there was a constant friction force. So once the object starts moving in region C, the friction force is constant, but it's a moving force, or a moving friction. So in region A, we had static friction. And in region B, region C, we had kinetic friction. So what the heck is region B? Region B is this point where if I exceed that peak and get it moving, it transitions from static to kinetic. Now you'll notice I gave it a little flick. I gave this a flick and it started to move. Then I stopped it, right? When I stopped it, right, so it was moving, it had this much force of gravity. I got it moving, so it kept moving, but then I stopped it and I got it back to this point where it was static friction. And then I gave it a little push that got it over the peak. And then it was in its kinetic friction zone. So when I give it a little click, a little push, I got that force to overcome that peak static friction, and once it overcame it, it started to move, but that kinetic friction is actually less than its peak static friction. So once you get it moving, it's easier, it has less friction force to oppose its motion. Okay? I'm not sure if anyone, not that I'm condoning this, has ever drifted, right? Your tires are built on static friction between the road, right? Rubber on the tire to the road. Once you break that static friction, you have to slow down to get it to stick again. I don't know if you've experienced that on ice. If you accelerate it too fast, your tires lose that static friction, so you stop. And then you try to go slower, okay? You slower with your tire rotation. So static friction, kinetic friction, you can experience that on your tires. Maybe on a rainy day, you step on the gas too quickly, you come to a stop, you re-engage the tire in static friction, then move forward. The whole goal for drifting is to get those back tires past that static friction and into the kinetic friction. Now, if I hear of anyone establishing or practicing their friction, static and kinetic friction, because Ms. Plongenberg said, this is evidence, no, I do not condone it, okay? Especially on snowy days, right, where you start doing circles in the driveway. No, don't do that on school property. Go find somewhere else to do that. Anyway, so test that out, but not because I told you to, okay? But you can see that practical region, that when you've exceeded that static zone, you've got less force required, or less friction force once you've got it in that kinetic or sliding phase, okay? I'm hoping that's helping you decide or discern between two types of friction, static friction and kinetic friction. So my next video is going to try to make a connection between your friction force and your normal force. Okay, your friction force and your normal force. All right?